Welcome to Chapter 20, podcast number 3. All right, this podcast is going to be all about the introduction of Gibbs free energy and then Gibbs free energy change, right? Delta G, so G and delta G in here. Right? And this is finally going to answer our question of whether a reaction is spontaneous or not mathematically, right? Delta H and delta S give us a pretty good idea, but we're not 100% sure until we calculate the Gibbs free energy change of a reaction. So free energy, which is given the symbol of G, which is named after Gibbs free energy, so I get where that G comes from, right? Free energy G has a relationship to enthalpy and entropy there by showing that G is equal to H minus TS, right? But really we want to care about the change in those things, and so delta G is equal to delta H minus T delta S. This is probably going to be the most important equation in all of thermodynamics right there. Right? This relationship is going to tell us whether a reaction is spontaneous or not. If delta G is less than 0, which another way of saying that is if we have a negative delta G, then the reaction is spontaneous. If we have a positive delta G, right, or a delta G greater than 0, then our reaction is non-spontaneous, the way that it's written. All right, if we reverse a reaction that's spontaneous, it becomes non-spontaneous. If I reverse a reaction that is non-spontaneous, it becomes spontaneous. If our delta G is equal to 0, then this is the case where we're at equilibria, right? It means that remember, spontaneous reactions are going towards equilibria, non-spontaneous are going away from equilibria. So if it's in between those two, then we're at equilibria, right? We're not driving our reaction one direction or the other. Okay, we've probably seen figures something like this before, right? And when we've been talking about enthalpy changes of things, right? Here I have my reactants and my products, and they are showing the free energy along the y-axis there. If my reactants are higher than free energy than my products are, right? When I go from having reactants to products, right, notice that my Gibbs free energy is going to be going down, right? Meaning that I'll have a negative delta G. If my reactants have lower free energy than the products, then my Gibbs free energy is having to go up, right? And so my Gibbs free energy will be positive. And we know that if we have a negative delta G, if the reactants have higher Gibbs free energy than the products, then that's spontaneous. If my reactants have a lower free energy than the products do, we have a positive delta G, then that is non-spontaneous. So we've seen that delta G is equal to delta H minus T delta S. And this can be called the Gibbs-Helmholtz equation. Again, don't memorize the naming of it, right? It's just that Gibbs is Gibbs-Helmholtz. And so they came up with this equation. And like I said before, this is the most important equation in all of thermodynamics. So this is the equation that we're probably going to use most of the time in thermodynamics. This is one of those equations that I will give you on your exam. It probably won't be on your final exam, but by then you'll have used it so many times that I assume that it'll be stuck in your brain whether you want it to be or not. Right? Remember that spontaneous reactions are usually when we have delta H is negative, and usually when our delta S is positive, right? And now we know that it's always true when our delta G is negative, right? And that's because when I plug things into this equation, right, it depends on which one of those factors is playing the biggest role, right? Sometimes if we have like a phase change, our delta S, right, our entropy change is going to be really big. If I'm going from a liquid to a gas, I have a really big change in my entropy. And so that might be a really big number that's in there, delta H minus T delta S. That delta S might be a really big value, and it might, influence whether our delta G is positive or negative. But then there's other times where I might calculate a delta S, and it might be really small in comparison to the delta H, right? And the delta H is going to be the thing that's dominating it. And so maybe that's going to be what influences whether the reaction is going to be spontaneous or not, right? And so they all interplay with each other. And we actually have to calculate our delta G in order for us to see whether the reaction is spontaneous or not. We can't just calculate a delta H or a delta S. We need this equation in order for us to calculate the spontaneity of reactions. So this slide is entitled the standard free energy change, right? And remember, standard, right? That's where we see that little not symbol sitting next to things. And so usually at standard conditions, right, we're talking about things being at 25 degrees Celsius. And any and all gases that are present are going to be 1 atmosphere partial pressures. And any and all of our solutions are going to be 1 molar solutions that are present. We did this in chapter 6 for enthalpy changes, right? We did those at standard conditions, and we also can calculate our entropy changes at standard conditions, and then our Gibbs free energy now can be done at standard condition. All right, when we do things at standard conditions, that's great, right? We like to calculate things at standard conditions. Then what we're going to find is what happens when we're not at standard conditions. But initially we're going to start out with everything at standard conditions, and then we're going to tinker with it a little bit later on in the chapter. But if everything's at standard conditions, then we basically have our Gibbs-Helmholtz equation that looks identical, except now we just have those not symbols that are plugged in as well. So it's delta G naught equals delta H naught minus T delta S naught, right? Just saying that everything's at standard condition. And just like before, negative delta G, spontaneous, positive delta G, non-spontaneous, delta G is equal to 0. Is at equilibrium. All right, at the very bottom it says, right, this delta G, if it's at 0, the reaction is at equilibrium. I want you to note that this is any time you have a phase change, we are going to be at equilibria. Right? If you remember, right, when we had like our container of water, right, and some of that water, right, if you've got a bottle of water and it's sealed off, some of that water up in the top is going to be in the vapor phase. So it's going to be in the liquid phase at the bottom. There's an equilibrium there. There's a phase change. We're going from a liquid to a vapor, but we're also going from a vapor to a liquid, and it's at equilibria. Just note that anytime you see a problem, it's going to be when you have a phase change, put in that delta G naught is equal to 0. We're going to work a problem like that. I like to sneak them in onto exams to see if you pay attention to what I'm saying here. Mark that down in your notes as something important that's going to show up. All right, just like for our enthalpies, right, we could calculate the enthalpy of formation by doing products minus reactants. Right? And we did that. Like, that's how we get those values that are in the tables that you can look these things up. Again, I think this is Appendix B, pages 5 through 7, where you can look up enthalpies, entropies, and Gibbs free energies. You can do the same thing for a delta G of formation. Again, right here, I'm writing standing up, so it looks kind of funny. But this is just, right, products minus reactants. Doing that, we can find the Gibbs free energy of formations just like those. Again, you can look these up in tables. If you have elements, right, the values for elements are 0, and element values are 0 for enthalpies of formation. Just keep in mind that when you work these problems, entropies for our elements are not 0 values. They have to be positive for all of our elements. So when you're working enthalpies and when you're working enthalpies and Gibbs free energies, and you're doing products minus reactants, if you have an element and you can just say, okay, oh, that's 0, I know that one. But if it's entropy, do not put it down as 0 or you're going to get it wrong. Look it up in the table. If you're confused and you're like, is this going to be 0 or not? Just look it up in the table anyway. If it's 0, it'll say 0. If it's an entropy, it'll give you a value, right? It doesn't hurt to take the extra 2 seconds to look it up, just to make sure that you're not, goofing on it, right? You might as well just do that extra thing if you don't remember for sure which ones are 0, which ones aren't. All right, let's work a sample problem, 20-4. This is the sort of a problem that you'll easily see somewhere along the lines, although likely, right, what they're going to do is they're going to give you enthalpies and entropies or something like that, but you might have to calculate them. So what we're going to do here is we're going to calculate our Gibbs free energy change at 415 Kelvin for the reaction of ammonia plus some oxygens producing nitrogen dioxides and waters. All right, Number one, this is already balanced, which is nice, right? But if you are given a problem like this and it's not a balanced equation, you've got to balance your equation. All right, and then we want to see, right, after we calculate our Gibbs free energy change, is the reaction spontaneous? So what we're going to do is, because this reaction is at 415 Kelvin, which is given to us there, we have to calculate our enthalpy change and our entropy change, and then we're going to use our Gibbs-Helmholtz equation. All right, so entropy, enthalpy, and Gibbs free energies, they can be found in Appendix B there on pages 5 through 7, right? And so if I wanted to do the enthalpy change, I could do products minus reactants, right? And so we could do stuff where we say, okay, I have 4 moles of nitrogen dioxide times whatever the nitrogen dioxide enthalpy is, plus 6 moles of water times it, right? That's just doing that stuff that we've done in Chem 1. I'm hoping that we get that stuff, that we understand it. If you're struggling with those, right, let me know over office hours or something like that, and I will work through them with you, right? But in order to just kind of like speed this up, I'm going to say that we have our delta H naught for this, right? Our products minus our reactants is going to be negative 1133.6 kilojoules. All right, so make sure that you remember that there's a negative in there and that the units are kilojoules for that, right? Once we solve this worked out. So we're going to do the same thing with entropy as we did with enthalpy, products minus reactants, right? So we're going to go through that, having the balanced equation, putting in the right number of moles for each one of the products, each one of the reactants. Remember, these are entropies, so if we have any elements, they're going to be non-zero, so we have to look all those up. But we're going to end up with an entropy equal to 112.0, right? And that is in joules per Kelvin, right? However, delta H was in kilojoules. We need the units to agree. So I'm just going to go ahead and convert that. My delta S is going to be equal to, oops, and this was negative 112.0 joules per Kelvin. Let's not make that mistake. Is equal to negative 0.112 kilojoules per Kelvin. All right, so the reason that we did that is now we're going to plug that into our Gibbs-Helmholtz equation, where I've got my delta G is equal to our delta H, right? And so our delta H we found to be negative 1133.6 kilojoules, right? And then we have minus our temperature, which is 415 Kelvin, times our delta S, which is negative 0.112 kilojoules per kelvins. All right, so if we look at that, right, we are going to be able to cancel out our kelvins, and so our Gibbs free energy should be in, our Gibbs free energy should be in kilojoules. So we're going to get that our delta G is equal to negative 1087.1 kilojoules. Our delta G is negative, and the last part of this problem asks us, was this going to be a spontaneous reaction or not? Yes, it is spontaneous. All right, so as we've hinted at before, another way that we can calculate our Gibbs free energy, our standard Gibbs free energy, is by doing products minus reactants, just like we do for enthalpies and entropies. All right, but big note, we can only use this equation at 25 degrees Celsius. Every other temperature, you have to calculate your enthalpy, your entropy, and then use your Gibbs-Helmholtz equation. So only at 25 degrees Celsius can I use this, right? In the Gibbs-Helmholtz equation, there is a temperature factor that's in there. It is really reliant on your Gibbs free energy. Your Gibbs free energy, right, is really reliant on your temperature. Your enthalpy changes a little bit with temperature. Your entropy changes a little bit with temperature, but they actually change at the same rate. And since you're taking enthalpy and you're subtracting off T delta S, they actually they kind of counterbalance each other. And so we can kind of neglect that when we calculate those at other temperatures. But our Gibbs standard free energy, we cannot neglect temperature. And so we can use this equation only at 25 degrees Celsius, as we did on our previous sample problem when it was at 415 Kelvin. I had to do the Gibbs-Helmholtz equation. So this is only good at 25. And if you're not sure whether you can use this or not, go ahead and calculate enthalpy and entropy, and then plug it into the Gibbs-Helmholtz, and that'll give you the correct answer every single time.